Okay, so let's start with a regular two-dimensional function, y equals sine of x. Pretty simple. You have an input, you have an output. The input's on the x-axis and the output is on the y-axis. And if you plot all those values for y equals sine of x, you'll get this sine curve. Now, if you want to find the slope of the line at each x value, you take the derivative of the function with respect to x, and you get cosine of x. And for any x value, you can plug that into cosine of x, and you can get the slope of the tangent line at that value. So for example here, you take cosine of 0 equals 1. That means the derivative of sine of x at x equals 0 is equal to 1, which means that the slope of the tangent line to that curve at x equals 0 is 1. So for a multivariable function, instead of taking in one input and having one output, you have two inputs, an x input and a y input, and one output, in this case on the z-axis. So I've introduced a new third axis. So if you take a little slice of that function, of that surface, let's say at y equals 0, this reduces down to z equals sine of x because cosine of 0 is 1. And if you take the derivative of this with respect to x, you're going to get cosine of x. And I've plotted this curve right here. This is z equals sine of x. Now, let's say I take it at y equals pi over 4. Now, cosine of y is equal to cosine of pi over 4, which is equal to the square root of 2 over 2, which is approximately 0.707. So now this graph is going to be different. This is less than 1, and so the graph for this would look something like this. A little bit smaller, and the derivative would be different. You now have z is equal to square root 2 over 2 times sine of x. If we take the derivative of this with respect to x, you get dz over dx equals root 2 over 2 cosine of x. So it's the same thing except scaled down by a factor of square root 2 over 2. So this is where I introduce the concept of a partial derivative. Basically, if you have this surface right here and you're slicing it up at each value of y, what you're basically doing is you're creating a z versus x axis little slice of a function. This curve, I'll just kind of trace it out here. It would look something like, this, right? And what that's called is a trace of the surface at that y value. It's basically just saying we're taking the surface and we're drawing a line over it, like a contour line over a 3D surface. So a partial derivative is basically you're taking this function and you're taking the derivative of it, but if you're taking it with respect to some variable, you're treating the other variable as a constant. So for example, and I can erase this now, just to have more room, you have z equals sine of x cosine of x, right? If you take the partial derivative of z with respect to x, so treating y, sorry, this is not x, this is y. So if you're taking the partial derivative of this function with respect to x, that means you're treating y as a constant. So this is just going to be cosine of x, because we're still taking the derivative of this part. And then this is just a constant, so we multiply by the constant using the chain rule. Sorry, product rule, not the chain rule. So this is just going to be cosine of x, cosine of y. This makes sense because if we took, for example, this one, z equals sine of x, and we took the derivative, we get cosine of x. If we evaluate this partial derivative at y equals 0, we just get partial z over partial x I guess at y equals 0, write that down there, is equal to cosine of x. Whereas if I evaluate it like I did over here, I'll grab a different marker, at y equals pi over 4, then the partial derivative of z with respect to x at y equals pi over 4 is equal to root 2 over 2 cosine of x. So that's all the partial derivative is. It's basically the slope of the tangent line of a certain slice of a 3D surface. And yeah, that's about it. Just taking it up close so it's easier to see.